Let us talk about Clausius inequality today, and then we'll talk about Gibbs Duhem equation. And these two are very important thing in thermodynamics because Clausius inequality is just another form of Carnot's theorem. So Carnot's theorem says that efficiency of any engine is either less than, so when it is irreversible, it is less than the efficiency of a reversible engine. And if it is a reversible engine, all reversible engine will have same efficiency. So efficiency of an engine in very simple words, so is defined as the amount of work which has been done by the engine divided by the heat which it has taken. So that means how much amount of money you gave and how much amount of work was done. So based on the amount of corruption, the amount of work which is done will be less than the amount of funds which were released. So that's the efficiency. So if Q1 amount of heat was given and Q2 amount of heat was rejected by the system, then W by first law of thermodynamics can be written as Q1 by Q2 divided by Q1, which gives you 1 minus Q2 by Q1. So now imagine that you have a lot of reversible engines and all of them will have same value of 1 minus Q2 by Q1 irrespective of the material the engines are made up of, irrespective of the type of engine and things like that. Therefore, this Q1 and Q2 cannot be an extensive property, it has to be an intensive property. It is something which is independent of materials amount. So using that logic, for reversible engines only, the efficiency can be written as in terms of absolute temperature of the reservoirs, that is 1 minus T2 by T1, where T2 is less than T1. So T1 is hot reservoir, T2 is colder reservoir. But for irreversible engines, the efficiency is still this. For reversible engine, efficiency is this. And you see that 1 minus T2 by T1 is irrespective of the type of engine. So therefore, for all reversible engine, the efficiency is going to be same, which is Carnot's theorem. So now if I want to write this inequality in terms of these expressions, then it will be 1 minus Q2 by Q1 less than equal to 1 minus T2 by T1, which I can write as minus Q2 by T2 less than equal to Q1 by T1. So, well, minus will not be there because both of them have minus. And now I can write it as minus Q2 by T2 plus Q1 by T1, and this is greater than or equal to 0 if I keep it on that side. So 0 is less than or equal to this. Now Q1 is the amount of heat which is given to the system. So if I define Q2 also as the amount of heat given to the system, so you can imagine a composite engine where Q1 amount of heat is given to an engine and it rejects Q2, so it is minus Q2. But this Q2 goes to another engine where it becomes positive, so that's the amount of heat given to the system, and so on. So you can write it as, so then it will become positive. So Q2 by T2 plus Q1 by T1, and if you have more engines in the series, you can write this as summation of all Qi's, Ti's, I going from I to 1, which you can write as integration of dq by t. Okay, so what we got to is that dq by t is less than or equal to 0, and this is Clausius inequality. And now if you proceed from here, you can see that for reversible engine, you will write dq reversible divided by T. And because it is reversible, it will go to the same temperature, right? You can reverse it. So this becomes a closed integral, and that will be equal to 0 because it is reversible. And for reversible engines, this is equal to 0. The inequality takes equality. So what do you see now? You see in this equation that this thing is a exact integration, right? If you remember our Pfaffian integration in the first lecture. So therefore this quantity dq reversible by T becomes a state variable. So it doesn't depend on the initial and final path taken. It only depends on the states of initial and final positions, and this is called entropy. So entropy is a state variable. Okay, so after that we will talk about entropy when it comes to it in more detail, but now we have to talk about Gibbs Duhem equation. Gibbs Duhem equation, and before that we want to use the idea of homogeneous functions. So homogeneous functions are those functions which can be defined as, say, fxy is a homogeneous function, which is actually f of lambda x and lambda y. So this can be written as lambda into f of x and y. So that becomes a homogeneous function. So this is a homogeneous function, and depending upon the degree of it, so it can be lambda or lambda square or lambda to the power n, it is called that degree of homogeneous function. So because of extensive nature of internal energy is a homogeneous function of order 1, is the homogeneous function of order 1 or degree 1, whatever you want to call it. Okay, so why are we doing this is we will understand first with the example of homogeneous function. So let us say that we have a function which is f of lambda x, and this is a third order homogeneous function. So this is basically this. Okay, so now what will be the derivative of this? So let us do the differential of both on each side. So the derivative of this is going to be f dash lambda x, and we are differentiating with respect to lambda, not with respect to x. So then it is going to be f of lambda x into x, because we'll differentiate lambda x. So x is not a variable in this case, lambda is, which will go away, so you'll have x, and this will be equal to 3 lambda square f dash x. Okay, now if you assume that lambda is equal to 1, then it becomes x f dash x is equal to 3 x f dash x. So here, because fx is not a function of lambda, so it is just fx. So this I made wrong. So it will be x f dash of x, because I'm putting lambda is equal to 1, is equal to 3 f of x. Okay, so here you see that f of x is basically x by 3 f dash x, and this is Euler's theorem, Euler's theorem. That will be the right pronunciation of Euler. Okay, so remember this when we do that. And one more thing you need to remember is that this we have done for function of the order 3. So if it was 1, then it will simply be x into f dash x. And here we have taken one variable. You can take x, y, and z, so you will have partial derivatives like this, like that. So now let us do that for internal energy, and let us first do it by the first what we know, and then we'll do it using our homogeneous function concept. So u as a function of s and v can be written as, so u is a function of s and v. So du will be equal to del u by del s at constant v ds plus del u by del v at constant s. And you can also make it a function of number of particles, which we so far have not included. But so we only played with pressure and volume and temperature. We did not change the amount of matter in question. So if you change that, then that also becomes a variable. So in that case, it will become del u by del n dn, and this is at constant. So this is at constant volume and n, this is constant s and n, and this is at constant s and v. Okay, and by definition, del u by del s at constant volume and constant number of particle is temperature. And we are not going to prove it, but this is the definition of temperature. And del u by del v, which at constant entropy and constant number of particles, the change in internal energy per unit change in volume, with respect to change in volume, is the change, is the pressure. And this you will see from first law of thermodynamics. This you can, both of these. So well, second you cannot get from the first law of thermodynamics, but this one you can get from the first law of thermodynamics. This you can get from Clausius inequality. Why? Because if the volume is constant, then if you put du is equal to dq plus dw, and so dq is, you remember, by Clausius inequality for reversible processes, is equal to s. So this dq becomes ts. Okay, so this becomes tds, and this becomes minus pdv if we are talking about either gases or liquid or solid. So from that, if you keep volume constant, this goes away and you get del u by ds. So del u by del s at constant volume will be equal to temperature, and that's how it becomes the definition of that. And del u by del v, so if you keep s constant, then del u by del v becomes minus p. So these are the two equations, and basically we'll get that equation only. So du is equal to tds minus pdv plus mu dn, where mu is called chemical potential and mu is simply this term, which is del u by del n when you keep entropy constant and volume constant. And if you change the matter, the internal energy of that matter changes. So you can imagine that you have, say, 10 particles of gas molecules in a constrained volume of a container. So internal energy of that container is, say, U. Now you are not changing the volume of the container, but you put now 10 more gas molecules in it, right? So for now double number of molecules, the amount of space, the volume, has decreased now. So the probability of each molecule hitting the container walls and also interaction with each other is going to be doubled now. So then pressure is changing. Without changing the volume, the pressure changes. and that causes a change in internal energy because volume is not allowed to expand now. Okay, and you can also understand entropy. So entropy, you will see later when we discuss the statistical nature of entropy, is simply that if you have say 4 sites and you have 2 number of atoms, so these 2 atoms can sit here, so that is one configuration. You can have another configuration like this, you can have another configuration like this, and so on. So this chaos is created, the disorder is created because you have more number of sites and less number of people sitting there. And if you change this, and this is what you change by changing n, and therefore the internal energy changes, and therefore the rate of change of internal energy per unit change in the number of particles is called chemical potential. So this is the expression for du. Okay, so now remember this, I will write it here again. So du is equal to TdS minus PdV plus mu dN. This is equation 1. Now let us take the homogeneous identity of internal energy, and because of its extensivity, it is a function of, so you can imagine this to be a function of entropy, you can imagine this to be a function of volume and number of particles. So it is going to be simply lambda U S V and N, and lambda is 1 in this case. So it is known that lambda is 1 in this case. So it is one first degree homogeneous function, internal energy. So what we did with Euler's theorem was Fx was equal to x by 3 f dash x for an order of third degree homogeneous function. If it is 1 degree homogeneous function, it is simply x f dash x. Okay. So if it is f of x and y and z, then it is going to be x del f by del x plus y del f by del y and so on. Okay. So similarly, I can write du, sorry, u, not du, u, because it is fx. U is going to be now s into del u by del s plus v into del u by del v plus n into del u by del n, and of course when it is partial I am keeping the other things constant, vn constant, here sn constant, and here sv constants. So you know that del u by del s is temperature, so it becomes Ts, this becomes Pv, and this becomes mu n. So this is now u. Okay, this is now u. And now if I do the total differential of this du, then it will become TdS plus du is equal to TdS plus SdT minus PdV minus VdP plus mu dN plus n d mu. So now you see that so this becomes our equation 2, and you see that there are differences in equation 1 and 2. So what are the additional term? Because if this is true, then the additional term here should be 0. So TdS is there, PdV is there, and mu dN is there. So what remains is SdT minus VdP plus n d mu, and this should be equal to 0, and this is what is known as Gibbs Duhem equation. Gibbs Duhem equation, and what it says is that these properties, you cannot change temperature without changing pressure and chemical potential and so on. So these three are dependent properties. These three are dependent on each other, and that is the physics, that is the significance of Gibbs Duhem equation. Now what we need to discuss is potentials and Maxwell equations or Maxwell relations. Maxwell relation, Maxwell similar to Euler. So these people, Maxwell and Euler, are not just bound to thermodynamics. They are very great scientists and they have done a lot of things in physics basically, and this is one part which becomes a topic in the field of thermodynamics. So you know that if u is a function of two variable x and y, then del u by del x, and so del 2u by del x del y will be equal to del 2u by del y and del x. So it doesn't matter from which variable you differentiate first. The second derivative, if you're differentiating with respect to both variables, then this is an identity. Okay, and using this on four different potentials which are in thermodynamics, you get Maxwell relations. The first one is internal energy, and internal energy you know is TdS minus PdV. This is one potential. What are potential that we have discussed for when we discussed about conservative field in our first lecture. The second potential is enthalpy, which is U plus PV. Okay, U plus PV. So that is second potential. And third potential is Helmholtz free energy, which is U minus Ts, and Gibbs free energy is H minus Ts. So these are the four potentials. And in different regime, so once you have the potential, the divergence if it is a vector and gradient if it is a scalar gives you the force for that potential. Okay. So one by one we will go to the Maxwell relations. So first let us start with internal energy. So internal energy is TdS minus PdV. We are not talking about dN. So the amount of matter in the system is constant. That is not changing. So using that double derivative identity, del 2u by del x del y must be equal to del 2u by del y del x. So using this identity, we know that del t by del v, if you differentiate this twice with respect to so if we differentiate u with respect to t again, so del t by del v at constant s must be equal to minus del p by del s. At constant s must be equal to this at constant volume. Okay, so how are we getting this? So we are getting this by double differentiating the u function. Okay, so y by del s. Okay, now if you at constant volume, okay, and minus p is equal to del u by del v at constant entropy. Now if you take mixed derivatives, so then del t by del v must be equal to del p by del s minus at constant volume, and this is at constant entropy, and this is what is first Maxwell relation, which comes by applying this identity on the first potential. Okay,